Okay, so here, yeah, so let me see. So here we talk about the applying the Gauss law for the cylindrical symmetry. Uh, so here it says a section of an infinitely long and cylindrical plastic rod. So plastic mean it is an isolator. The charge on it are not free to move. So here there is a plastic infinitely long cylindrical plastic rod, and of course we also assume that it is thin. There is no thickness of it, so it's just a line. It's just a line for infinitely long, and there is charge on it. So it says there is a uniform charge density lambda over this rod. Okay, the charge distribution and the field have cylindrical symmetry. So to find the field at radius r, we can enclose a section of the rod with a concentric Gaussian cylinder of radius r of of radius r and height h. So actually, we define this is the Gaussian surface. So it is a cylinder. The axis is the same as the plastic rod itself. Okay, so the net flux through the cylinder from the Gauss law reduced to this thing. So let me try to explain why. So of course, this is a rod, and due to the symmetry, we would expect the E field are perpendicular to this rod and then pointing outward as it is a positive charge. If it is negative charge, the E field at any point are actually pointing to the rod itself. Here is positive charge, the E field pointing the outward and also perpendicular to the rod. So as much as this is a cylinder, there are three faces: the top face, the bottom face, and the side. For the top and bottom, for example, the top one, the DA should be pointing to the top. So DA and E are perpendicular to each other, which means that E dot DA will be 0. So there will be no flux contributed by the top surface. Similarly, the bottom face, DA pointing downward. So there will be no net flux contribute no net flux contribute to the net flux. There'll be no flux for the bottom surface contribute to the net flux of this Gaussian surface. So the only phase will be the side. Yeah. So here we assume the height of the cylinder is h. So you may ask, how high should we chosen? But finally, you will find that this h will be cancelled out, so it doesn't really matter how large this h should be. Okay, so now let's consider how to calculate the net flux for the side surface. Okay, so of course, when you try to write out the Gauss law, so it should be epsilon naught, and then E dot dA, and then equals Q in charge, Q enclosed. Yeah, so E dot dA, and also we assume that E is parallel to dA. We will also have dA pointing to the same direction. So this one will be nothing but EDA, and then E can be factored out, so it turns out to be something like that. So it should be like E epsilon naught times E times the surface area. This is the surface area. Okay, so the surface area of this side surface will be like you can try to cut this thing, and then you try to expand it, then it will become a rectangle. of course, the height of this rectangle will be the same as the height of this cylinder, which would be h. And then the width of this rectangle should be the circumference of the circle, which is 2 pi r. 2 pi r. So here we try to cut this cylinder, and then you try to explain it as a plane, so it will become a rectangle, and the area here will be h times 2 pi r. So before getting this expression, we write it as this is a. So this is epsilon naught e times a, epsilon naught e times a, which is this one. So we have a to be h times 2 pi r. So here we have a equals 2 pi r times h. So a equal this term, and then we plug in here. So we have epsilon naught e times 2 pi r h equals q enclosed. Q enclosed means the q enclosed by these parts. Of course, this is a line, so we will assume it has a linear charge density rather than a surface charge density. So this linear charge density is lambda. So lambda times the height will be the total charge. This is a linear charge density times the length will be the total charge within this Gaussian surface. Okay, so here we can clearly see that we have h on both sides, so we can cancel it. And we can move over other terms on the left side. So on the left side, we only have e, and then 2 pi epsilon naught r will be here, 2 pi epsilon naught r. And then we have lambda on the top. So this is the closed form expression for this structure, which is an infinitely long cylindrical plastic wad, like this. Yeah. Yeah. So it relates to, so this one is a constant. It relates to the linear charge density and also the distance from the rod to the point you concern, because this expression tells you that suppose you pick a point on the Gaussian surface, the distance from this point to here should be small r. So it relates to the distance from the point you concern to the rod, of course the perpendicular distance, yeah, or the shortest distance between this point and the rod. And then it also related to the charge. If the charge is larger, if the charge density is higher, then the E field should be stronger. So yeah, it really makes sense. And if it is farther away, then the E field will be weaker. So also makes sense. Okay, so if no question, I'll move on. So here we talked about planar symmetry. So in the previous slide, we talked about cylindrical symmetry. So this is the planar symmetry, and later on we may also have a spherical symmetry, maybe. I'm not sure. Yeah. So here, here we have a non-conducting sheet, which means that the charge on it is not free to move. It's not free to move. So it says a portion of a thin means no thickness, infinitely large, so infinitely large, non-conducting sheet with a uniform positive surface charge density. It can be negative. So you just change this value to negative for negative charge surface density. So yeah, so a sheet of thin plastic wrapped uniformly charged on one side can serve as a simple model. Here apply the Gaussian Gauss law. So here we assume this is from a 3D view. So and this one is the something like the cross section. So you regard this one. This one is the non-conducting sheet, and then with a positive charge. So it will generate the E field in the space. So here we try to also apply a Gaussian surface, a cylindrical Gaussian surface. But previously, when we talk about the conductor is very large, but here it is very thin. So here, this is the Gaussian surface, the cylindrical Gaussian surface. So this is a circle face, this is another circle face, and this is the side. So in the cross section, you only see a rectangle here. So this is one side, this is the another side. Okay, so as much as we know the E field is perpendicular to the plane, so it point to the left side for the left part, and it points to the right side on the left on the right part. So there will be no net thrust contributed by the side, as previously mentioned. So the left face and the right face will contribute to the net thrust of this Gaussian surface. So here we try to write out the Gauss law, and then this net flux can be separated into two parts. This is from the left part, and the other one is for the other part, for the right part. Okay, so as much as E is parallel to the area vector, and also E is uniform, so this is nothing but E times A. We don't really need to go through the surface integral. So we just simplify the surface integral into a simple product. And so as this one, so we have two EA because we have E on the left side and also E on the right side. So we have two EA, and then here we also assume it should be the surface charge density sigma. So when we consider the Q enclosed, so it should be this part, which is sigma times A, sigma times A. So here we assume that this is thin. This is thin. This is thin, which means that the thickness should be 0, should be regarded as 0. But here, of course, it cannot write it as 0, so it draws something out. Otherwise, it cannot draw the plus sign to indicate the positive charge. But yes, but here you should regard it as a very thin sheet, so that there should be one phase to contain the charge. So we only have sigma times A, sigma times A. Okay, so here we can also cancel the A on both sides. And then here we have 2 epsilon naught E equals sigma. So it turns out to be E equals sigma over 2 epsilon naught, which has the same expression as this one. And as I mentioned, using the integration will be complicated, and using the Gauss law, the calculation is as simple as this one. Okay, so next we try to have multiple conducting plate. So for conducting plate, which means that there will be induced charge. The electron or the charge on the conductor are free to move, can be attracted or repelled by some other charges. Okay, so here we assume we have 2 conducting plates placing in parallel. So we have one plate and another plate. Here we assume the plate has some thickness. So in this case, there are some positive charge on the left surface and some positive charge on the right surface, but no charge in between. And another one, we have some negative charges. And here we assume that both of the charge density, the surface charge density are the same, even though this is a positive charge, this is a negative charge, but the density will be the same. And as much as this is infinitely large, we will say the total charge are also the same. Okay, so here, for the left one, we try to consider it separately first, and then we try to place them together. So when we consider figure A, try to forget the other one first. So for this one, it will generate the E field pointing to the left side on the left, and then pointing to the right side on the right. Okay, and then from this calculation, we will say that the E field has a magnitude of a sigma 1 over 2 epsilon naught, sigma 1 over 2 epsilon naught. And so as this one, sigma 1 over 2 epsilon naught, although this is a negative, but here we only consider the magnitude. So here, the E field point to the left side on the left, the E field point to the right side on the right. But here, since the charge is negative, so the E field points to the right on the left, and then the E field points to the left on the right. Okay, so here we try to place these two conducting plates together. So in this case, this is positive charge and this is negative charge, and opposite charges will attract each other. So for the left plate, all the positive charge will go to the right surface. And then on the right side, all the negative charge will go to the left surface. Since these charges and these charges attracting each other, there will be no charge on the left surface on the left rod, and then there will be no charges on the right surface or for the right plate, not rod. Okay, so in that case, you can consider we try to add these two figures together. So on the left part, it is like the E field pointing to the left side plus the E field pointing to the right side, and then the magnitude are actually the same pointing to the opposite side, so they perfectly cancel. So there will be no E field pointing to the left side, no E field pointing to the left side. No E field on the left side, I mean. And then similarly, there will be no E field on the right side, because we have E field pointing to the right side and then E field pointing to the left side with the same magnitude. So they perfectly cancel each other. So this part E is 0. And in the middle part, which is like we add this one with this one. So the E field have the same magnitude and point to the same side. So the E field should be this one plus this one plus this one. Oh, but actually this one you will consider that it should be like the magnitude is double, because all the charge going to the right surface, so it is like when you just consider this part and this part, the density becomes double. The density becomes double. And when you consider this surface and this surface, it is like the density becomes double. Okay, so here we try to add them together in the between part. So it will be like the total E will be E plus E minus will be you just multiply this one by 2, because this one plus this one, these two numbers are the same. So it's like 2 times this one. 2 and 2 cancel each other. It becomes 2 times sigma 1 over epsilon naught. And then we rewrite the new surface charge density to be sigma rather than sigma 1. So it turns out to be sigma over epsilon naught. Okay. So yeah, so here, if we have have two infinitely large plate with charges, but with opposite sign, and the charge amount are the same, it will generate uniform E field in between. No E field will be outside. Yeah, so this is the point. Because sigma is a constant, epsilon naught is also a constant. So this is a constant E field in between the parallel charge plate. Okay, so here is a sample problem. Okay, so it says portion of the two large parallel plates non-contact sheet, each with a fixed uniform charge on one side. The magnitudes of the surface charge density are sigma plus for the positive charge sheet, and sigma minus to be this value for negatively charged sheet. Find the electric field to the left of the sheet, so which means the EL, and then between EB, and then to the right, ER. So we try to find EL, EB, and ER. Okay, so let's try to calculate E plus, and E minus first. E plus and E minus first. E plus means the E field generated by the plus plate, the positive plate. So for the positive plate, E plus point to the left side for the L part, and then E plus point to the right side for the B part, because B and R are relatively right to the positive plate. So E plus point to the right side for B and R, and point to the left side for the L. But for the negative plate, L and B are relatively left to the negative plate. So, and as much as this is a negative charge, so E minus point to the right side for L and B part, and E minus points to the right side, point to the left side for the R part. So we have this one. So this one tends to cancel something. This one would add up. This part cancel something. Okay, so let's try to calculate what is the value of E plus. E plus will be nothing but sigma over epsilon naught, or should be 2 epsilon naught, because it will generate E field on both sides. So it will be sigma plus, I would say sigma plus. Sigma plus is a 6.8 times 10 to the minus 6 over 2 times 8.85 times 10 to negative 12. So this number will be 3.84 times 10 to the 5th Newton per Coulomb. And then for E minus, it is similar. So it is a sigma negative over 2 epsilon naught. Okay, so it is 4.3 times 10 to minus 6 over 2 times 8.85 times 10 to minus 12. So this number will be 2.43 times 10 to the 5th power Newton per Coulomb. Okay, so for the left part, we should have E plus minus E minus. So EL should be E plus minus E minus, which should be 1.14 times 10 to the 5th power Newton per Coulomb. And then it is point to the left side. And then for the B part, EB should be E plus plus E minus. So it will be 6.27 times 10 to the 5th power Newton per Coulomb. And it should point to the right side. And ER should be also be E plus minus E minus. So it should be 1.41 times 10 to the 5th power, which is the same as EL, but here the direction should be pointing to the right side. So, any questions? So, okay, so finish off this one. So if no question, we will move on. So in chapter 21, we talk about the Shell Theorem. And at that time, what I told you that is I cannot really tell you the reason why it is true, but here with the Gauss law, I can tell you why the Shell Theorem is true. So if you still remember, the Shell theorem has two statements, and the first statement is that a shell of a uniform charge attract and or repel a charged particle that is outside the shell, as if all the shell are charged, will concentrate at the center of the shell. So for the outside part, you regard as you are outside. So you also define a Gauss surface larger than the sphere, larger than the sphere. Okay, so when we try to apply the Gauss law for S2, then we can quickly find that writing out the Gauss law, epsilon naught times the surface integral of a E dot dA and then equals Q enclosed. So this is Q enclosed, which is small q, and on the left side, it is a sphere, so it is like epsilon naught 4 pi r squared and then times E. So due to the spherical symmetry. So it turns out it will be like that. So it is nothing special. It feels like all the charge are at the center. So yeah, so that's the first statement of the Shell theorem. And the second one is that if a charged particle is located inside the shell of a uniform charge, there is no electrostatic force on the particle from the shell. So here, we talk about inside a shell rather than outside of the shell, outside the shell. So here, of course, we will try to assume that S1 is smaller than the radius of a sphere. So here, this is S1. And when we try to apply Gauss law to the S1, so on the left side, we still have epsilon naught surface integral of a E dot dA. And this part will be nothing but epsilon naught 4 pi r squared times E. And then on the right side, Q enclosed will be 0 because all the charge are outside the Gaussian surface. So this one is nothing but 0. Okay, so this stuff are constant and are not equal to 0, which means that E equals 0, which is this statement. So this is the second statement for the Shell theorem. And using the Gauss law, we can simply explain why the Shell theorem introduced in chapter 21 are correct. The two statements are correct. Okay, so next, this is another interesting case. So here we talk about a non-conducting sphere, so that it has a surface density. So just now when we mentioned a conducting sphere, then all the charge will be at the surface. But here we assume that this is a isolated sphere or non-conducting sphere, so that here we just assume that the charge density over this sphere is uniform. So we have a uniform volume charge density. So we define this is a rho. This is rho. So we try to determine the E field outside and also inside the sphere. So for outside, it is nothing special. It is nothing special. For the outside case, when you try to define the Gaussian surface outside the sphere, then the charge enclosed is the total charge Q. So applying the Gauss law for this Gaussian surface, you will end up with a similar expression. E equals 1 over 4 pi epsilon naught times Q over R squared when small r is larger than or equal to capital R. However, for the second case, if we consider the point which is inside this non-conducting sphere, which means that R is smaller than capital R, then things will be a bit more complicated. So here is the Gaussian surface smaller than the sphere itself. So the Q enclosed is not all the charges. So here we try to determine the Q enclosed divided by the volume of the Gaussian surface. As much as the density is uniform. So this is the density inside the Gaussian surface, and this is the density for the whole sphere. So this is the total charge. This is the total charge. This is the total charge. This is the charge enclosed by the Gaussian surface. This is the volume of the whole sphere. And then this is the volume for the Gaussian, this is the volume enclosed by the Gaussian surface. So this is small r is this one. And then the capital R is the radius of the sphere. So this one. And as much as the density is uniform over the whole sphere, which means that these two densities should be the same. Okay, so here we can, of course, cancel the pi, cancel 4 over 3, cancel 4 over 3. So we get the expression Q enclosed equals Q times small r cube over capital R cube, like this. And then we can apply Gauss law for this Gaussian surface. On the left side, it is, as always, epsilon naught times E times 4 pi R squared. So it is epsilon naught times the E field times the surface area. And then for Q enclosed, what we get is this expression. So we plug in this one here. And then we can do some cancellation because we have R squared. So we can cancel with cube down to R cube down to a single R. So finally, we move over these three terms over to the right side. So on the right side, we have a 1 over 4 pi epsilon naught here. And then we have R on the top, and then R cube on the bottom. R cube on the bottom. So it look like this. Okay, so of course this expression is different from this one. So this is for outside part, this is for inside part. Yeah, but still the dimension should be the same. The dimension means this is the first order of the length, and then this is the third order of the length. So the length will cancel out down to a square in the denominator. So which matches this one, which matches the dimension of this one. So even though it's a small r in the numerator and a capital R cube in the denominator. So we will have similar equation for the magnetic field in chapter 29 for the electric flux density for the in chapter 29 using the Ampere's law. So we may consider it later on, but yeah. But this is a quite important result, I say, because it is an interesting way to apply the Gauss law. Okay, so here, this is the expression. This one is for the outside the sphere. This one is for inside the sphere. And if we try to draw it out, this one you can say it is proportional to 1 over r squared, or inversely proportional to r squared. And for this one, it is proportional to r, because all the when you try to draw it out, you usually consider r is a variable, but other things are fixed value. Of course, 1 over 4 pi epsilon naught is a constant. But when you consider this line, usually Q is a constant. Capital R is also constant because you don't really want to change the size of the sphere. So all the other terms are constant. Only R, small r, is a variable. So E is inversely proportional to R squared when R is larger than or equal to capital R. And here it is proportional to R for the inside the sphere. Okay, so when you try to draw it out, so this is linear increase, and then reduce in an inverse square way, like this. So the maximum point will be at this point. Okay, so here we will have one additional example. So this is quite interesting. Quite interesting. So yeah, maybe this is actually one of the, I'm not really sure whether it is one of the selected problem, but yeah, actually let me just show it to you because it is quite complicated. Okay, so the volume charge density of a solid non-convex sphere of a radius r and varies with a radial distance r, as given by this expression. So the density is not uniform anymore. The charge density, the volume charge density is not uniform anymore. So it increases with the radius. Okay, so the first question is, what is the sphere's total charge? So for the total charge, which means that the sphere has a radius of r. And as much as the charge density is not uniform, you cannot write the total charge Q is rho times V. So this is not correct because this is not uniform. And in that case, what we really need to do is to go for a integral, and it is a triple integral. So maybe it's look quite difficult for you, but yeah, we call this sphere a V, but it is actually a triple integral. Okay, so rather than using the Cartesian coordinate dx, dy, dz, we will use the spherical coordinate. Spherical coordinate. Okay, so if you have interest, you can, or maybe you may learn the spherical coordinate in the calculus class later. But yeah, but if you are interested now, you may check it on the Wikipedia. It will show you what is a spherical coordinate, how to define it, and how it relate to the Cartesian coordinate. It is something like you have the distance from that point to the origin is r, and then there are some angle defining by you try to project it on the xy plane. So x, y, z, like this. So you try to project it on the xy plane. So this is one of the angle, and then you have another angle like this is another angle. This is another angle. We call it phi. So in that case, here we should have the triple integral, and then let's write out rho. Maybe we call this one rho s. So later on, we can plug in rho s to be 35.4 pico. Okay, so we have a rho s times small r over capital R. So this is rho. And then for dv in the spherical coordinate, it should be r squared sine theta dr d theta d phi. And then, of course, this is a complete sphere. So dr, we should integrate from 0 to capital R for a whole sphere, okay? And then for theta and phi, theta is considering from 0 to pi. And then for phi, this is phi, this is theta. Okay, theta is from 0 to pi, so it is the angle between the z-axis and the point connecting the origin and the point. So it can be between 0 and pi, 0 and pi. And for the phi, it is the angle from the x-axis to the projection of it. So it can come from 0 to 2 pi. Okay, so we need to do this triple integral, but fortunately, the expression is separable, which means that we can write it as the multiple of a function of r, function of theta, and function of phi. So it makes the integration quite simple to work with. So actually, phi s is a constant, and then capital R is also a constant, so that we can move it out. And then in total, we have r cubed. So we need to do it for dr from 0 to capital R. And then we have sine of theta. So we have sine of theta d theta. We need to do the integration from 0 to pi. And then for d phi, we don't have any phi in it, so that you can regard it as a 1, a function 1, from 0 to 2 pi. So all these integration are quite trivial to work with. So this one is nothing but r to the 4th power over 4 is a polynomial, and we evaluate from 0 to capital R. And for this one, the antiderivative is a negative cosine of theta evaluate from 0 to pi. And then for this one, it is the easiest one. Integrating 1 is phi, and then evaluate from 0 to 2 pi. So this one will be r to the 4th power over 4. This one, cosine of theta is, cosine of pi is -1, cosine of theta is, cosine of 0 is 1. So this is 2. And then for this one, this is nothing but 2 pi. Okay, so finally we have rho s over r times r capital R over 4, and then times 2 times 2 pi. So it turns out to be, so we can see 2, 2, and 4 will be cancelled. And then this one and this one will also be cancelled. So the answer will be pi rho s r cube. So this is the chart, and of course we can just plug in the number. 3.14 times rho s is 35.4 times 10 to the -12 power, and then times r cube is 0.056 cube. Okay, so this is 1.95 femtocoulomb. Okay, so this is actually the answer. And for part B, what is the E field of the magnitude E? So if you try to, so this is the sphere, and then you try to define the Gaussian surface with R to be 0. So the surface is actually 0. So you can see that a phi is 0, which means that the E should also be 0. So this is very trivial. And for part C, when R equals to capital R over 3, it will be yeah, we actually need to calculate the Q enclosed first. The Q enclosed is not the same as this one because here we need to consider R over 3 instead of the full R. But the only difference is that we just change this R to R over 3 and nothing changed. So this one will be like rho s over R and then integrating R dr. Maybe we call it dr prime, R prime cube from 0 to capital R over 3. And then the remaining terms are the same, integrating sine of theta d theta from 0 to pi, and then integrating a 1 d phi from 0 to 2 pi. So this one also gives you 2 pi, this one also gives you 2, this one gives you R over 3 to the 4th power or over 4, something like this. So the expression will be like, let me see. It should be still we have rho s over R and then R to the 4th power over 81 times 4 times 2 times 4 pi. So sorry, 2 pi. 2 pi. So these 2, 2, 4 will cancel each other. This one cancel down to R cube. So finally, we have a rho s over 81, and then we have pi also R cube, like this. Okay, so here we can apply the Gauss law. So we have a epsilon naught times 4 pi R squared E equals Q enclosed. So we have epsilon naught times 4 pi R squared E equals pi rho s R cube over 81. And here, this R should be R over 3, R over 3. So finally, we can get E to be rho s, or maybe we can still, let me see. Oh, I think here maybe we try to keep here should still be the small r, so that we try to get an closed form solution rather than try to get an expression like this rather than substituting the r to be capital R over 3. So we have the expression like pi let's see. We still should have pi rho s and then times R cube. Although we know that R should be capital R over 3, but we don't substitute it yet. We just leave it to be small r. So we have the expression like this. And finally, we will get the expression will be like a rho s rho s times r squared over 4 pi epsilon naught r when r is smaller than capital R. So this is the closed form expression when small r is capital R over R. So yeah, and so maybe we just stop here and we continue next time.